Welcome to Chemistry. This video is a flipped classroom video intended for the teaching of Zumdahl's 7th edition chemistry textbook's Chapter 8, Chemical Bonding. It is not a review video. This is a semi-in-depth lesson that covers the first half of Chapter 8, which is everything up to modeling. It is not meant to be watched in one sitting. In fact, there are links in the description below to the point in the video where each section of the chapter begins. Another disclaimer: please do not rely solely on this video to succeed in Chapter 8 in AP Chemistry. The following resource, not this one, this resource, your lovely 7th edition Chemistry Zumdahl textbook, must be opened and thoroughly read in order to do well in AP Chem. More importantly, it is advised that you complete the practice problems in this book, as the practice problems will help you discover what concepts you remain unclear on. This video covers the following chapters. 8.1 Types of Chemical Bonds. 8.2 Electronegativity. 8.3 Bond Polarity and Dipole Moments. 8.4 Ions, Electron Configuration and Sizes. 8.5 Energy Effects in Binary Ionic Compounds. 8.6 Partial Ionic Character of Covalent Compounds. There are several key things to look out for in this presentation. Key vocab words you must know are in red. Important definitions, explanations, or phrases are bolded. The textbook section you can refer to for the slide on screen can be found in the top right corner of the slide. At the end of each section, there will be a slide that indicates what basic concepts you ought to be able to know or be able to do by the end of this section. Also, feel free to pause the video at any point in time or go back to rewatch past concepts. Alright, let's get started. Types of Chemical Bonds, Section 8.1. Chemical bonds. We're not referring to intermolecular forces. That is covered in Chapter 10. Here we are referring to the interaction of atoms to form molecules. So, why do bonds form? Like everything in chemistry, the formation of bonds is so that the system can reach a favorable state. In this case, the lowest possible energy. A state where the lowest possible energy exists for a system is the most stable. Okay, so then when do bonds form? Of course, bonds don't just form randomly. One atom won't bond with another atom across the universe at 4 a.m. in the morning because, I don't know why this is in the script. But bonds form when the total energy of the aggregate is slower than that of the separated atoms. What does that mean? It's when two atoms together at a certain distance have a total energy lower and therefore more favorable than the total energy when they are separated and floating around in space being lonely. Here's some important vocab. Bond energy. That's the energy required to break the bond. Bond length. That's the distance between the center of the atoms when the total energy of the system is minimal. So what types of bonds are there? Well, there is ionic bonding, when one atom loses electrons which another atom gains, resulting in one positive and one negative ion that are attracted to each other due to their difference in charge. This resulting compound is called an ionic compound. This usually occurs when a metal reacts with a nonmetal. Metals like to lose electrons, nonmetals like to gain electrons, all because they want to enter a more favorable state. Then there is covalent bonding. Instead of losing or gaining electrons, the atoms are more communist. They share the electrons equally between the two nuclei. This is nonpolar covalent bonding. The atoms are very communist, the electron sharing is equal. Then there is polar covalent bonding. This is an intermediate between ionic and nonpolar covalent bonds. The electrons are shared between the nuclei, but not equally. One atom has the electrons for a larger percentage of the time than the other atom. This is like siblings sharing toys. We share the same toys, but one of us tends to have it for the majority of the time because, one of us is more dominant. We'll talk about atoms dominating later when we talk about electronegativity. Here's the key concept: Coulomb's law. Coulomb's law is used to calculate the force between two charged objects, an attractive or repulsive force. In chemistry, we use it to calculate the attraction between ions of opposite charge, determining the strength of the attractive force. The formula is the force F, which is equal to K Q1 Q2 over R squared, where K is a constant, Q1 and Q2 are the charges of the two ions, and R is the distance between the ions. Mathematically, we see that the greater the magnitude of the charges, the greater the magnitude of the force will be as the numerator increases. At the same time, the greater the distance between the ions, the weaker their force will be as the denominator increases. This will come in handy later, especially in Chapter 8.5. Here we have a key diagram that I can almost guarantee you will see on a test somewhere in some form. This is a graph of bond length versus the energy of the system. Note that this graph is for two hydrogen atoms. The optimal state of the atoms is where the energy is minimal. On the graph, it is the bottom of the dip. The first thing to understand is that the energy of the system here is a combination of the net potential energy and kinetic energy of the atoms. We also have to realize that zero energy occurs when the atoms are an infinite distance apart. Note, by Coulomb's law, an infinite distance will generate an infinitely small attraction or repulsion force. Another key trait of this diagram is that the energy increases rapidly and approaches infinity when the atoms are very close to each other. This is because the small distance greatly increases the Coulombic force of attraction or repulsion, as the nuclei of the atoms are extremely close, and in this case, for hydrogen, the two positive nuclei are unbearably close, making the state extremely unfavorable. And so, the bond length of the hydrogen-hydrogen bond occurs at the place that is most favorable, when the system is at minimal energy, or the bottom of the dip in the graph. And we see here that the bond length is 0.074 nanometers, while the energy of the bond is negative 458 kilojoules per mole. That's all for section 8.1. Electronegativity, section 8.2. Electronegativity is the ability of an atom to attract shared electrons to itself. In section 8.1, I talked about how in polar covalent bonds, electrons aren't shared equally. Why? Because one atom is more electronegative than the other, having a greater ability to attract shared electrons. Here's a diagram of hydrogen fluoride. On the left, in A, the hydrogen fluoride molecules are just floating around, and we see that the hydrogen end of the molecule is positively charged, while the fluorine end of the molecule is negatively charged. When placed in an electric field in B, all the molecules are suddenly oriented in the same way, with the hydrogen end, the positive end, oriented toward the negative plate. The charged end of the hydrogen fluoride molecule result from fluorine being more electronegative than hydrogen, thus attracting the electrons unequally and being the more negative end of the molecule. So, we have electronegativity values, obviously, so that we can quantitatively compare them. That genius guy Linus Pauling, who won several Nobel Prizes, thought this up and created this chart. You absolutely do not need to memorize the values. However, you do need to know the general trend that electronegativity increases across a period from left to right, and it decreases going down a group. As a result, fluorine is the most electronegative, while francine is one of the least electronegative elements. So how does electronegativity help us with determining bond polarity? We can use the following rules to determine bond polarity. However, sources differ on the exact values. If the difference between the electronegativities of two atoms is greater than or equal to 1.7, then the bond is ionic. Logically, this means that one atom is more electronegative than the other, completely hogging the electrons, resulting in more of a donation situation than an unequal sharing. If the difference is less than 1.7, we can say that the bond is covalent, or that there is a certain degree of sharing occurring. If the difference is between 0.4 and 1.7, this sharing is still unequal, hence the bond is polar covalent. If the difference is less than 0.4, the sharing can be assumed to be equal. The bond is nonpolar covalent. Note that just because the bond is polar doesn't indicate that the molecule is polar. Bond polarity is not the sole factor in determining molecule polarity. On a more general note, we can say that as the electronegativity difference increases, the bond type goes from covalent towards less covalent. More importantly, we must remember that almost every bond is both covalent and ionic in character. A more covalent bond is less ionic in character, while a more ionic bond is less covalent in character. That's all for section 8.2. Bond polarity and dipole moments, section 8.3. Recall this diagram from section 8.2. Here we have hydrogen fluoride, and there is a polarity that results in one end of the molecule being slightly positive, while the other end is slightly negative. This is known as a dipole moment. A dipolar molecule is a molecule with an atom with a center of positive charge and another atom with a center of negative charge. This molecule is said to have a dipole moment. Di means two, and pole, well, there's a positive pole and a negative pole, two poles. How do we draw diagrams to indicate this dipole moment? Well, here's a very grainy image of one way we can diagram the dipole moment of hydrogen fluoride. But before we explain diagramming, you have to know these symbols. The one on the left is lowercase delta, and the one on the right is uppercase delta. We use positive delta and negative delta to indicate poles and their charge. So don't be surprised when you see deltas on dipole diagrams. There are three ways to diagram. The first way is just to indicate with the deltas which ends are positive and which ends are negative. Looking at the electronegativity charts, we see that oxygen is more electronegative than hydrogen. Thus, it has the electrons for more time and is generally more negative than the hydrogens. We see a negative delta on the oxygen end and positive deltas on the hydrogen ends. Note that the sum of the charges is zero. The molecule itself does not have a charge. The second way you can diagram a dipole moment is by using an arrow. The arrow points in the direction that electrons are more attracted to, the more electronegative side. Meanwhile, the other end of the arrow has a cross on it, taking on the idea of the plus symbol. This end is more positive or less electronegative. This diagram also has charged plates to orient the molecule. You can also draw charged plates to indicate molecule orientation. The negative pole will be oriented towards the positive plate. This final diagram is usually computer generated. It is a colored gradient where the blue, cooler colors indicate the areas where the electrons frequent relatively less, while the red, hotter colors indicate the areas where the electrons frequent more often. Thus, the red ends are more electronegative, and bluer ends are less electronegative and oftentimes more positive. Here's all three diagrams side by side. Well, we know that water is a polar molecule with polar bonds. But what about a non-polar molecule with polar bonds? Check out carbon dioxide. There's still a dipole moment. We can see that the oxygen are more electronegative than the carbons. But note in figure B that there are two arrows going in opposite directions with equal length and strength. These two dipole moments cancel each other out, and thus there is no positive or negative end of the molecule. Note in figure C that the gradient is relatively even. It goes from red to blue and back. The diagram can be said to be symmetrical. Thus, the molecule is nonpolar. And that's all for section 8.3. Ions, electron configuration and sizes, section 8.4. We've seen ions in previous chapters. They shouldn't be new to you. The importance of ions in this chapter is related to ionic compounds, or nonmetals reacting with a representative group metal. Together, ions form binary ionic compounds. The valence electrons of the elements become noble gas configurations because noble gas configurations are more stable. To achieve this, nonmetals gain electrons to have the valence electron configuration of the next noble gas, becoming an anion, while metals lose electrons to have the valence electron configuration of the previous noble gas, becoming a cation. When scientists speak of ionic compounds, they generally are referring to the solid state. Why? Because in a solid state, the ions are packed tightly together in a generally organized fashion that maximizes attractions between ions and minimizes repulsions between ions. When packed in such a way, the molecule is generally more stable. Meanwhile, in a gaseous state, ions interact with each other rarely, becoming extremely unstable floating around in space. You should know already how to predict the formula of ionic compounds. The basic concept here is that there needs to be enough of each ion such that the total charge of the molecule is neutral. Here's a cheat diagram from Google that tells you how to get the formula quickly. You should already know how to do this. Okay, I'm going to flash something on the screen now, and I want you to memorize it quickly. Bam! Alright. No, I don't actually want you to memorize this. Why? Because there's no reason to. These ions can be determined with the handy-dandy periodic table. Elements of group 1 are generally 1+, because they lose a 1 electron to take on the form of the previous noble gas's valence electron state. Elements of group 2 lose 2 electrons to become 2+, and group 3 is the one exception. Boron isn't really metallic, so only aluminum behaves with the trend, losing 3 electrons to become 3+. Meanwhile, groups 6 and 7 gain 2 and 1 electron respectively to become anions, and okay, you guys get the gist, I'm done here. Moving on, we are talking about ion size now. Here's a bunch of ions and their sizes. Notice that there are trends with ion size. Ion size increases down a group due to greater number of filled electron shells resulting in greater radii. Across a period, funky things happen because some ions lose and other ions gain electrons. According to Zumdahl, it's complicated. Here's a very important trend. It's on isoelectronic ions, ions that contain the same number of valence electrons. Here we have 5 ions: sulfur, chlorine, potassium, calcium, and gallium. All 5 of them have the valence electron configuration of the noble gas argon. How do we know which element will have a larger ion size? It's simple. The more protons, the smaller the ion size. Why? Because increasing the number of protons increases the effective nuclear charge, which decreases the radius of the ion. That's all for section 8.4. Energy effects in binary ionic compounds. Section 8.5. Alright, this section is going to be a bit long. So, what's this section really about? Lattice energy! Lattice energy is the change in energy when ions are packed together to form an ionic solid. Or, the energy released when an ionic solid forms from its ions. This lattice energy is generally negative because a release of energy is exothermic, or a negative change in energy. Cool. Okay, so now that we know what lattice energy is, how do we find it for ionic compounds? The first important thing to note is that lattice energy problems can only be applied to single atoms in the gaseous state. We're not looking at polyatomic ions here. The way to find lattice energy we can find via the Born-Haber cycle. This cycle is an approach to analyze reaction energies thanks to Jason Born and, not Jason Born, Max Born and Fritz Haber, 2 Germans. Apparently some guy named Fajans, also figured this out, but he doesn't get credit. I find it difficult to understand the Born-Haber cycle cold, so we're going to get into it through an example. Our example is lithium combined with fluorine gas creating lithium fluoride. So, we start with a given equation. Lithium plus 1/2 fluorine gas creating lithium fluoride. And we find out that this equation has an enthalpy of negative 617 kilojoules per mole. We want to get from that equation to our lattice energy equation, where the ions of lithium and fluorine combine to form lithium fluoride. So what do? Our first step is to convert all our participating species to 1 mole of the element in gaseous form. Lattice energy only works for elements that are in the quantity of 1 mole and in gaseous form. We take the solid lithium and convert it to gaseous lithium. This is also known as the sublimation of solid lithium. And we can find that the enthalpy of sublimation for lithium is positive 161 kilojoules per mole. So, we have lithium solid converted to lithium gas, which has an enthalpy of 161 kilojoules per mole. Okay, now we convert the fluorine from F2 to 1 mole of fluorine gas as an element. This is the dissociation of fluorine gas. The energy for dissociation of fluorine is 154 kilojoules per mole, the energy required to break 1 fluorine gas molecule bond. But we don't have 1 molecule, we only have half a molecule, or half a mole. So we divide the energy by 2 to get 77 kilojoules per mole. So now we have the fluorine gas converted to 1 mole of fluorine gas element, and its enthalpy is 77 kilojoules per mole. Great! Now we move on to step 2. Step 2 is to convert these gaseous 1 mole elements to their ionic form. Lithium is in group 1, it tends to lose an electron to become a cation. This is the ionization of lithium, and the first ionization energy of lithium is 520 kilojoules per mole. Now we add that equation to the processes, and it has an enthalpy of 520 kilojoules per mole. Nice. So now we need to get fluorine into its ionic form. Fluorine is group 7, it tends to gain an electron to become an anion. This is the formation of fluorine ions. And gaining of electrons can be found with the electron affinity of fluorine atoms, which turns out to be negative 328 kilojoules per mole. So now we add the formation of fluorine ions to the processes, and an enthalpy of negative 328 kilojoules per mole. And voila! We have all the processes involved to go from the overall equation to the lattice energy. Actually, it's more like the lattice energy along with all the other processes sum up to create the overall equation. Here we see all the equations and their energy changes, and note that the species in the equations cancel out, so that the overall equation is all that's left. The processes must sum to give the overall process, otherwise it is invalid. So, we set up our equation with the overall energy change on the left and the sum of the other energy changes along with the mysterious lattice energy on the right. And we solve for the lattice energy, which turns out to be negative 1047 kilojoules per mole. Bam! Okay, so back to the Born-Haber cycle. The Born-Haber cycle indicates that the enthalpy of the formation of a compound is equal to the sum of 5 processes. This is specific to lithium fluoride, but first, there is the enthalpy change of atomization of lithium, turning lithium into gas and a singular molecule. Then we ionize it. Then we atomize fluorine, and then we do electron affinity to fluorine, and last but not least, there's lattice energy. Alright, I don't really like thinking about it in 5 steps, so I condensed it into 3. In general, you have to convert the species to gaseous state and make 1 mole of each of the elements first. Then, these elements need to be converted to ions. The cation requires ionization energies, and the anion requires electron affinity. And then we have lattice energy at the end. Yay! Okay, so just to give a visual diagram of what happens so you don't freak out when you see a visual diagram on the test, it looks like this. Notice that each step is included, and that it is a cycle, not a unidirectional process. Okay, so here we compare the cycles for magnesium oxide and sodium fluoride. Note that the lattice energy for magnesium oxide is way larger in magnitude than the lattice energy for sodium fluoride. Why? This is because the ionization energy and the electron affinity for magnesium oxide is much greater than that of sodium fluoride. With magnesium and oxide, we're dealing with ions that have greater charge magnitude, 2 plus and 2 minus, while sodium fluoride has smaller charge magnitude because it's 1 plus and 1 minus. It takes much more energy to add and remove 2 electrons than to add or remove 1. So, in general, compounds containing ions with greater charge magnitude are going to have more negative lattice energies. Here we have a rough reference to Coulomb's law. Lattice energy is equal to K Q1 Q2 over R. Realize that with a larger charge magnitude, Q1 and Q2 would be greater, and thus the lattice energy would increase. At the same time, having greater charge magnitudes would increase the attraction between the ions, and have a smaller radius between the 2 atoms, so there will be a smaller R and as a result a greater lattice energy. Remember, greater ion charge magnitude, greater lattice energy. Woohoo! That's all for section 8.5. Partial ionic character of covalent bonds, section 8.6. Alright, so this section is super short. It really is just, help, how can I distinguish between an ionic bond and a polar covalent bond? Great question. Unfortunately, there's probably no such thing as a totally ionic bond. Thus, in theory, all bonds are covalent to a certain extent, going back to the covalent character versus ionic character diagram from section 8.2. And so, we can calculate the percent ionic character of a bond because, after all bonds are ionic to a certain degree also. The formula is the measured dipole moment divided by the calculated dipole moment. Just know this simple formula. I've never seen it show up, but that doesn't mean it won't show up for you. Well, now we have a problem. Since everything is ionic or polar to a certain degree, how the heck do we differentiate between them? Well, Zumdahl says, don't worry. Any compound that conducts an electric current when melted will be classified as ionic. And that's all for section 8.6. Well, that's it for part 1 of chapter 8, chemical bonding. The second part involves creating models of molecules, which is too much information to include in the same video. This video was created by Raymond and Atirath Dhara, and all information in this video can be found in the Zumdahl 7th edition chemistry textbook. Happy studying, and good luck on the AP exam.
That's all, folks.